This is Dr. Holt. This lecture is on simple harmonic motion. When you have a spring here that's attached to a mass, the force that's going back is always going to be in the opposite direction that it's being deflected. So if the object's being deflected to the right, then the force coming back is going to be to the left. So that's why you get F is equal to negative kx. Now if you hang an object from a spring, let me draw a picture of that. If you have a spring hanging here, and I take a mass and I attach it to that spring, when I do that, the spring will deflect. We'll do the deflection in blue. If I draw a free body diagram of that, then you will have mass times gravity coming down. And then the force coming up is going to be k times x. So basically that means if you know the deflection and you know what mass is being applied, then you can find the value of k just by setting the summation of forces in the y direction equal to 0. Now also we know if we set force is equal to mass times acceleration and set that equal to minus kx, divide both sides by mass, we can find the acceleration is going to equal to minus kx divided by the mass, or the second derivative of your position equation in respect to time. Alright, there's two equations you can use here. The first one to find your position, you can use A, the amplitude times the cosine of omega t plus alpha. Now that's going to be useful when you take a spring. Let me draw another picture here. You have a spring that's sitting here, and now you deflect it with a mass or with a force and pull it down. We'll hang a mass from it. And then release it. If you release it from when it's fully stretched, I would recommend using this equation here, x is equal to a times the cosine of omega t plus alpha. However, when t is equal to 0 and you find out the position is going back through the equilibrium point, I'm going to recommend that you make your life easy and just use a, or x position is equal to a times the sine of omega t. And if you do that, you're not going to have to deal with phase shift at all. Alright, so either one of these equations are useful because basically a cosine and sine function are identical except for a phase shift. Alright, a couple things to note here. When your mass is fully stretched to one end, in that case you're going to get a maximum acceleration going back the other way. Your velocity is going to equal 0. You're going to have your maximum potential energy. When you go back through the equilibrium point, your acceleration will reach 0. You're going to reach your maximum velocity. Obviously, you're going to reach the maximum kinetic energy. Now, anywhere in between here, you're going to have a combination of kinetic energy and potential energy. Alright, skip ahead. Let's go to this. Once you have your position equation written as demonstrated above, all you have to do now is take the derivative of that. You take the derivative of that, the first derivative, you're going to get your velocity equation. So again, you're going to do that with the chain rule. Omega is going to come back out. The derivative of cosine is going to need negative sine. That's why you're going to get negative omega a sine of omega t plus alpha. Now if you take the derivative of that, you're going to get your acceleration. When you do, you'll have to pull out another omega. So that gives you negative omega squared times amplitude times the cosine of omega t plus alpha. So that's going to give your acceleration. That is useful to give your acceleration at any point in time. This equation is good to give your velocity at any point in time. Now you can also go back and say acceleration is equal to negative omega squared times x. That's also going to give your acceleration at any point in time. Now also, if you take this and then solve for omega, you can find out that omega is going to be nothing more than the square root of k, the spring constant, divided by the mass. And that's going to be useful when you have one of these that's unknown, and the other two are given, you can find the other variable. If you want to find V max, it's just going to be omega times maximum amplitude. If you want to find acceleration, omega squared times amplitude. Or you can write it as V max is the square root of k over m times amplitude, or maximum acceleration is km times a. Now, when you do your period, you have two ways to do this. You can do 2 pi over omega, or if you want, you can do 2 pi times the square root of mass divided by the spring constant. Now, when you do frequency, all you're basically doing is you're inverting your period. So you can do that as omega over 2 pi, or 1 over 2 pi times the square root of k over m. So I've just inverted this back to get this. Okay, let's look at one problem here. This problem was worked in class. Here you're given an equation. Let me grab my notes here. Okay. With this equation here, your amplitude is going to be this value right here. Now, you don't necessarily have to change this back to meters. You can leave it in centimeters. That's fine. Amplitude here would equal to 4 centimeters. Okay, now to find your frequency, you can go back and say that frequency is equal to omega over 2 pi. Now, typically, what all I do is I just remember that period is always equal to 2 pi divided by omega. I usually do period first, and then just invert that to get your frequency. Now, omega is going to be this value right here. That's your angular frequency. So to find I'll find my period first. My period t is just going to equal to 2 pi divided by pi. Pi's will cancel out. That gives me 2 seconds. So my period will equal to 2 seconds. Now to find frequency, just be 1 over 2 seconds. So that gives me 1/2, or 0.5 hertz. Okay, to find the velocity acceleration at any time, all you're going to do now is take the first derivative of this equation here. Velocity here would equal to 4, and I'm going to do this with the chain rule. So I'll take 4 times, now the derivative of cosine is going to be negative sine times omega times t plus my phase shift of pi over 4. And I take the derivative of what's inside here, which is going to leave me a pi. So to simplify that, that gives me negative 4 times pi times the sine of pi times t plus my phase shift of pi over 4. That'll give me my velocity at any point in time. And then to find my acceleration, all I have to do now is take the derivative of my velocity equation here, and I'll bring that down here and then bring it back up. Alright, to find that would give me negative 4. And I'm going to do this part first. You take the derivative of that, that's going to give you the pi, so that makes it a pi squared. The derivative of sine is going to be positive cosine pi t plus my phase shift of pi over 4. That's going to give my equation for acceleration at any point in time. Now if I want to find my position, velocity, or acceleration at t equals 1, to find my position, I'm just going to take this equation here, put in t as 1. If I want to find my velocity at any point, I just put t in as 1 here into my velocity equation, and acceleration the same way. Alright. Now, if I want to find maximum speed, the easiest way to find maximum speed is take omega and multiply it by the amplitude. And omega in this time is going to be pi times my amplitude is 4. So it would be 4 pi, and my units here would be centimeters. To find maximum acceleration, all you have to do is omega squared times my amplitude. And to do that, that would be would be pi squared times amplitude, which would be 4. And again, that would be in centimeters per second squared. Okay, now this, when I find maximum acceleration, maximum speed here, obviously speed, we're going to make that positive. So if you get a negative value here, then you're going to change that because it's going to be positive because you're dealing with speed. Find maximum acceleration. Remember, that's only going to give you the magnitude value here, not going to give you the direction. Determine displacement of the object between t as 0 and t as 1. You're going to take 1, you'll put it back in this equation, find out the position when you're 1. Put 0 in for t, find the position when t is equal to 0. Subtract the 2, that will tell you your displacement between t is equal to 0 and t is equal to 1. Okay, in the second problem here, I have a particle. It's moving along the x-axis in a simple harmonic motion. Starts from the equilibrium position at t is equal to 0 and moves to the right. The amplitude is 2. The frequency is 1.5 hertz. Show that the position of the particle is given as this value right here. Okay, so what we want to do here to prove this is correct, we go back to frequency is equal to omega divided by 2 pi. So we can say that 2 pi times our frequency is equal to omega. Now you're given your frequency is 1.5 hertz. So 1.5 times 2 pi will give me a value of 3 pi. So 3 pi will represent my omega. Right, and that validates this value right here. Now, one of the reasons that this is modeled using the sine function, as mentioned earlier in the video, at time equals 0, you're starting at equilibrium position. There's no reason to use a cosine function, again, because you're going to deal with phase shift if you do that. So here we'll start with the sine function. Alright, now let's see what we have here. Let's see, we got the amplitude is 2, so we got that right there. So really we have the equation right now. So we know immediately that x is going to equal to 2 centimeters times the sine of omega t, which gives me my 3 pi times t. Alright, next question. Determine the maximum speed and the earliest time when t is greater than 0, which this particle has this speed. Alright, the easiest way to find V max is just go back and say omega times a, which will give me 3 pi times the amplitude, and we'll keep this into 2 centimeters. That's going to give me 6 pi. So 6 pi meters per second is going to be my maximum velocity. Alright, to find out when that occurs, I need to take the derivative of my position equation. And if I do that using the chain rule, I will get velocity is equal to negative, oh sorry, not negative, so we're doing the sign. Will be 6 pi times the cosine of 3 pi times t. Alright, we'll set the velocity equal to 6 pi. So when I do that, I'll get 6 pi is equal to 6 pi times the cosine of 3 pi times t. Divide both sides by 6 pi, that gives me the value of 1. I'm going to move down to give myself a little bit more space to do that. So let me see if I can grab this right here. Drag it down to there. So now I divide by 6 pi, that gives me 1. So 1 is equal to the cosine of 3 pi times t. Okay, now we'll take the inverse cosine. Inverse cosine of 1 is equal to 3 pi times t. So now when you think about this, the inverse cosine, that's going to give you a value of 0. So you know when you first start out, since you're going through the equilibrium, you're going to reach your maximum velocity. Now you want to ask yourself, well, when will it occur again? Well, when you could also consider this being plus or minus when I do this, so we think about what's the inverse cosine of -1. That's going to give me a value of pi here. So if I take pi and set it equal to 3 pi over t, divide both sides by 3 pi, that's going to give me 1/3 second equal to t. Now let's go back and think about the period for 1 second, and this I think is going to help explain something. We know that period is equal to 2 pi over omega. Now we've defined omega as 3 pi, right? So t is equal to 2 pi divided by 3 pi, which will give me 2/3 of a second. So what that basically means is, if you start here, this is t is equal to 0. The object's moving to the right, so it's going to come down, it's going to turn around and come back. That would make time right there equal to 1/3 of a second. Now it's going to go back down to the other end, and now it's going to return to here. So now t is equal to 2/3 of a second, and that's what's taking place here. If you think about it in terms of your period, it logically makes sense and it agrees exactly with what occurred here, where t is equal to 1/3 of a second. So again, when you're going through the equilibrium point at t equals 0, you're moving to the right, you're going to turn and come back. That's going to represent 1/3, and then when you come back again, that's 2/3. That's one incomplete period. So half your period would be when your velocity would also be max too, going back the opposite direction. Alright, let's look at the rest of this. Determine maximum acceleration, earliest time which this particle has its acceleration. Well, then we can go back and say omega squared times the amplitude will give me my acceleration. And we know, again, that's going to give me 3 pi squared times 2. That's going to give me 9 pi times 2. Sorry, 9 pi squared times 2. That gives me 18 pi squared, which will give me 178 centimeters per second squared. Alright, let's think about where that's going to occur. We know we're going to get maximum acceleration. Let's go back to the picture here. You can always get maximum acceleration when you reach the maximum end here and actually come to a stop where your velocity is 0. That's going to be your maximum acceleration. So here we're going back. Let's see, we're moving to the right. So when I get back to this point here and stop, my acceleration is going to be going back the other direction here. So what we're going to do is we're going to let that acceleration be negative because we know it's moving back to the left. So we take the value that we have here, we take it negative 178 centimeters per second squared. That's going to be our max acceleration at that point here. Now, there's two ways to do this. You can think about it in terms of your period if you want to. If you know it takes 1/3 time to go back to that point at this end here, then when at t is equal to 1/6 of a second. Because from here to here, you travel 1/6 a second. You come back to here, which would be 1/6. That gives you the 1/3, and then you go back here another 1/6. Now, if you don't like that, all you have to do is take the derivative of your velocity equation here, set it equal to negative 178, and solve, and you should get 1/6 of a second. Alright, now the last thing says determine the total displacement between t is equal to 0 and t is equal to 1. Again, I won't work this in details, but all you're going to do to find total displacement is put 1 second into here, find your position, put 0 back in here, find your position, subtract the 2, and that will give you your displacement between that time interval. Alright, I hope this video was useful. Worked a couple problems. Again, the problems aren't too bad, mainly just takes practice. Remember, you can always take the derivative of your position equation, that's going to give you your velocity. Take the derivative of your velocity, that's going to give you your acceleration. Alright, best of luck.